we're started here. Okay, so this is derivatives of trigonometric functions. Again, by the end of this chapter, you should be able to find the derivative of anything I throw at you. Anything. Could be trigonometric, could be logarithmic, could be exponential, could be polynomial, could be rational. You could, by the end of this chapter, you're going to be able to find the derivative of any possible function I could give you, or any combination of function that I could give you as well. Let me get her going. Right. One more. Come on this way. Come on. Come through this door. I'll give you guys a topic to discuss. Rhode Island, neither a road nor an island.
You're right.
The first part is the hardest part. I did not know the music stuff, but like it's easy to guess. It's easy to guess on them, okay? And then the first part is like matching. So like it's like the genres, and then you have to match them to like certain things that they did socially. Like, and some of them are confusing. Because they're all on drugs. And then it gives you an example. Then it'll give you like Mark, Beyonce, Jay-Z. Oh my God, I hate that. And you have to say which one it, like where it came from. I didn't know. Are those Snoop Dogg?
All right, and we're back. Rhode Island, neither a road nor an island. That's from SNL. That's from a. You ever anybody watch like classic SNL skits?
Yeah. Wait, what did you say?
It's from an SNL sketch. It's Mike Myers. They do like a coffee talk, and they're like they say, then like he starts crying, like fake crying, and he says, "I'll give you a minute. Discuss. Rhode Island, neither road nor an island. Discuss." Well, okay, maybe that's just me. Yes.
Did you see the old Italian court soakers one?
No.
You did not see that one?
No. Let's. I don't even want to go there. All right. Before starting this section, it might be a good idea to review trigonometry. Now let's talk about trigonometry, shall we? I feel like I should restart. Is everybody here today? No. He's gonna have to watch this video. This is the same trig identity sheet that you got last year, right? The exact same one. So I'm gonna give you another copy. Because I bet you didn't keep it. I was going to say, maybe it got burned somewhere along the way.
It got burned.
Malfunctioning.
All right, here are the trig identities that you learned last year. The exact same sheet. Now the trig identities that you see here. Now, I am not authorized to give you any sort of reference sheet. Okay, I actually asked the Stark State guy, like, am I allowed to give you guys like formula sheets on anything? And he said I can give you formula sheets on quizzes, but I can't give you formula sheets on tests. But here's what I did. As I was making all of the quizzes and tests last year, I made the derivatives ones that we used a lot. The ones that you would just memorize naturally rather than having to like do like flashcards or something like that. Okay. Now, before starting this section, we might need to review these trigonometric functions and identities in particular. It's more important to remember that when we talk about the function f to find all real numbers by f of x equal to sine x, it's understood that sine x means the sine of the angle whose radian measures x, obviously. If we sketch the graph of this function, we get this. That's sine of x, right? Down there on the bottom. We did that last year. You didn't do that in Algebra 2. We don't teach graphing sine and cosine, but you definitely did that last year in pre-calc. Graphing trigonometric functions. We see the zeros at, and this is sine, the zeros at 0, pi, 2 pi, and on the other side, and all, repetitions of those things. 0, pi, 2 pi, 3 pi, 4 pi, all forever and ever. And the same thing in the negative direction as well. Now, if I were to ask you about the derivative of sine, I would want to look at what is going on with the slope, because the slope is truly the derivative, right? The slope is the derivative. Well, let's take a look at some key parts of what's happening with the slope. What's going on with the slope? These are some unique values. What's the slope at each one of those points? 0, right? So if I were to graph the derivative, that would mean there would be a 0 for the derivative at all of those points. At all of the peaks of sine, peaks or valleys of sine, there are zeros in its derivative. Okay, so those are at pi over 2, 3 pi over 2, and so on and so forth, right? Okay, so I have an infinite, it's going to keep having zeros, isn't it? Take a look here and here. What do you see for all of those slopes? What are all of these slopes? What does that look like? What do you think the slope value is there? 1. What about these? -1. So in between those zeros, it's going from -1 to +1, right? The derivative is going to have a value anywhere between -1 to +1. Does it get any bigger than 1? Nope. Does it get any smaller than -1? Nope. That's interesting. That sounds familiar. Ranging from -1 to +1 with zeros at pi over 2, 3 pi over 2, and so on, and negative pi over 2, and negative 3 pi over 2, and so on. Here's the graph of the derivative. What is that called? That's cosine. That's actually cosine. The derivative of sine is cosine. Look at the zeros. Look at the zeros. A 0 here, a 0 here, a 0 here, a 0 here, and all points in between. It's varying from -1 to +1. It's going as high as -1 and as low as, as high as +1 and as low as -1. So all in summary here, the derivative of sine is cosine. We're going to start to make for ourselves, like, compiling ourselves a list of trigonometric derivatives. So the derivative of sine is cosine. The derivative of sine is cosine. So let's use that as a derivative. Let's take a look at this one. If I wanted to find the, come on, there it goes. If I wanted to find the derivative of y, where y is equal to x squared times the sine of x, what are we going to have to use to differentiate? X squared times the sine of x. What do you think we're going to have to use? Emphasizing times. The product rule. I am going to have to use the product rule. Do we all see our f and g? The two pieces of the product rule. Let us remind ourselves of the product rule. F prime g plus g prime f. That's the product rule. Okay, so let's do that. F prime g. What's f prime? 2x times g times the sine of x plus g prime. What is the derivative of sine? Cosine. Times cosine x, plus cosine x times the original f, x squared. From this point on, all we do, and honestly, this is really it, we find the derivatives using our, all of our rules that we had, and then we just try to reduce them down if possible, using any identities that we could possibly use. So for example, this one, here's how I could manipulate it. Maybe I write 2x sine x plus x squared cosine x, and see if there's any identities to come up with. So let's look at our sheets. Let's see if we've got anything. We might be tempted to try to use sine squared plus cosine squared, but This is not sine squared plus cosine squared. That's just sine x and cosine x. I honestly don't see any relationships that I could use. And in that case, you're done. I remember, I was just watching the video of last year. We could use this. We could say x times the quantity, 2 sine x plus x cosine x. Sorry for the poor handwriting there. 2 sine x plus x cosine x, but that really doesn't do anything either. So why not just leave it? 2x sine x plus x squared cosine x. Okay. Now, I'll tell you this, and this is going to happen a lot from here on out. The book goes into great depth on the proofs of all of these things and the demonstrations on why the things are that they are. But I'll tell you right now, if I tried to explain these to you guys, it would go way over your head. It would probably take me half the period. So I think it's okay, and if you'll allow me to say it's okay that we just accept these things to be true. These things, again, we're just going to have to memorize. Like, I remember back when I did this homework assignment, like way back when, last year, I had this page, I printed out this page, and I had it there, like, as I did the work, so that I could make sure that I knew what was going on. So d over dx of cosine x, the derivative of cosine, see, the derivative of sine was cosine. The derivative of cosine is actually negative sine. The derivative of cosine is negative sine. Not inverse sine, negative sine. That makes sense. Derivative of cosine is sine, or sorry, excuse me, derivative of sine is cosine, derivative of cosine is negative sine. It's almost like it's the reflection on sine. But tangent, always weird. Tangent x, if I have the derivative of tangent, it's secant squared x. Secant squared x. Jaden. Do I need to write your pass, Jaden? What? Do I need to write your pass, Jaden?
Oh no, this is my free period.
Okay, got it. Turn your box then. Good.
Yeah.
Thanks for stopping by.
Yep, you're welcome. Have a good weekend, Mr. Weber.
You too. Happy Halloween. Okay, so we have the derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of tangent is secant squared x. Those two right here are listed right here. Those are not different. Those are the same thing. And if we talk about the derivative of sine, cosine, and tangent, we should also talk about the derivative of cosecant, secant, and cotangent, right? Because those are just the reciprocal trigonometric functions. If I have the derivative of remember, secant is 1 over cosine. Cosecant is 1 over sine. So if I have the derivative of cosecant, it's negative cosecant x cotangent x. If I have the derivative of secant, it's secant x tangent x. And if I have the derivative of cotangent, is negative cosecant x. Or sorry, negative cosecant squared x. Let me remind you guys that I think it's important to remember that, say, for example, we've got secant squared x. We all remember what that notation means? Secant squared x. A lot of people always frustrated, okay, where does the squared go? Like, how does that work? Remember that this notation, all that notation is saying is this, secant x squared. That's all that's saying, right? You have two secants. Secant squared x is really like saying secant of x squared. So why don't we just write it like this? Because then it looks like you're squaring the x, okay? So just know that secant squared x is saying two secants on x multiplied together, okay? Not this. That looks like secant of x squared. All right, so let's find some derivatives. Let's work on it. Let's differentiate. Let's differentiate f of x where f of x is secant x divided by 1 plus tangent of x. And then we're going to talk about for what values of x does the graph have a horizontal tangent. That's going to be very important later on, like in chapter 4, talking about horizontal tangents. All right, so our function is secant x over 1 plus tangent x. What do we think we're going to have to use? The quotient rule. I've got a fraction here, so I've got to be using the quotient rule. Remember, that's f prime g minus g prime f. F prime g minus g prime f, all divided by g squared. Okay, the derivative of the first. Okay, that is going to be, remember, this is f and this is g, right? The top is your f and the bottom is your g. So, look back to my last page here. Oh, that's funny. I don't even have it in my notes because I ripped it out to use the homework. So, I guess flip back to my last page of my notes. What is the derivative of secant? Secant x tangent x. Okay, so that means I've got secant x tangent x. I like to put things in parentheses just to make sure I have things organized correctly. Secant x tangent x times the original g times 1 plus tangent x. I think I probably should put this like down here because this is going to be a long numerator. Minus g prime f. Now, the derivative of the bottom. What happens with my 1 in the bottom when I find the derivative? Goes bye-bye. Goes away. So then it's the derivative of 1 gone. The derivative of tangent. Okay, derivative of tangent. Oh, it's right there. Secant squared x. Secant squared x times the original numerator. Okay. All divided by g squared. Now, again, I hesitate to FOIL this. I would not FOIL that. You could. Look at you, pass. No? Okay, good. So here's what I'm going to do to try to reduce this down. From this point, it's like, okay, let's hope to throw something at the wall and see what sticks, right? Remember doing like trig identities last year? And it was just kind of like walking around in a dark pitch black room, and so you don't really know where you're going. Just kind of like feeling around, like hoping it comes out in the end. It's kind of like the same thing. You kind of just have to like work with it to see if anything cancels out, right? So here's what I'm going to do. I see that in both of my terms. So what I'm going to do is I'm going to factor that out. I'm going to factor out a secant x. And I'm going to distribute in this. So this is going to be tangent x plus tangent squared x minus secant squared x. Okay. I remove this secant x all the way out. And I've got tangent x plus tangent squared x minus secant squared x, all divided by 1 plus tangent x squared. What's up? What's going on?
Where did we get the tangent squared?
I did this. And tangent x times tangent x got us tangent squared x. Does that make sense?
Yeah.
I kind of did two steps at once. I removed the secant x and I distributed it to that. Okay, I can use a trig identity now. Try to find it. There is a trig identity hidden in there. There it is. The 1 plus tangent squared. I'm going to put it in right over here, kind of sideward. 1 plus tangent squared x is equal to secant squared x. Now, how can I use this? Because this is tangent squared minus secant squared, right? And if I bring this over to the other side, this is going to be 1 is equal to secant squared minus tangent squared. Sorry, sometimes when I write these things, the x goes away. But you get the idea. This is 1 is equal to secant squared minus tangent squared. I've got tangent squared minus secant squared. Oh, okay, what if I do this? What if I just multiply by -1 to everything? -1 is equal to negative secant squared plus tangent squared. Okay. -1 is equal to tangent squared minus secant squared. And there I have it. There's my identity. That is right there. That is all equal to -1. So yeah, this is actually can be reduced down to secant x times tangent x minus 1, all divided by 1 plus tangent x squared. Now, I could try to distribute in that secant back again to see if there was any other identity I could use, but spoiler alert, there's not. We could try to say secant x tangent x, but secant x tangent x is not on there. You know what we could possibly try to do? What is secant? Secant is 1 over cosine, right? Secant is 1 over cosine. I'm just seeing. This is where I stopped last year in my notes, but sometimes there's this hidden 1 over cosine. What is tangent? Sine over cosine, y over x? Tangent is sine over cosine? Okay, that doesn't do anything. I thought maybe this might cancel, right? I thought maybe that might cancel. But unfortunately, it's 1 over cosine. And if I tried to distribute that in, it would just be like sine over cosine squared minus cosine, 1 over cosine. So that doesn't do anything. So I stopped for a good reason. There was my answer. That was it. Yeah, just go ahead and turn it into the box. You guys are good. James, are you done? Okay. So there's my answer there. Secant x, tangent x minus 1 over 1 plus tangent x squared. Okay. Trigonometric functions are often used in modeling real-world phenomena, in particular vibrations, waves, elastic motion, other quantities that vary in a periodic manner can be described using trigonometric functions. In the following example, we will discuss an instance of simple harmonic motion. Even like temperatures end up as a periodic, like almost trigonometric curve. You know, think about it. Temperatures go up, like in terms of like general over the course of the year. Oh, the temperatures go up, they go down, they go up, they go down, they go up, they go down. Okay, an object at the end of a vertical spring stretched 4 centimeters beyond its rest position. So think about a spring. We're stretching it 4 centimeters beyond the rest, and then we're releasing it. What's it going to do? It's going to go up and down again, right? So that's what's going to happen. That's what we're looking at here. When I release the spring, it goes up and down at time 0. Its position function is s is equal to f of t, which is 4 cosine t. 4 times cosine t. Find the velocity and acceleration at time t and use them to analyze the motion of the object. Okay, if I want velocity, what do I have to do to the position function? Take the derivative. Find the derivative. Okay, so s prime is equal to v. Okay, s prime. What's the derivative of 4 cosine t? Now, let me ask you this question. Does the 4 go away? No. If it was 4 plus cosine t, it would go away. But because it's a constant multiplied by the function, it stays. So what's the derivative of 4 cosine t then? Well, what's the derivative of cosine? Negative sine. So -4 sine t. -4 sine t is the derivative of 4 cosine t. That's the function that models the velocity. Okay, well, we're asked to find velocity and acceleration, so that means double derivative of position, or the derivative of velocity is acceleration. Okay, what's the derivative here? What's the derivative of sine? Cosine. Does the -4 go away? No. -4 cosine t. Now, I would like to bring up the page in the book because they actually give, I should have copied it in, but they give a really cool illustration of, no, not here, a really cool illustration of the graphs of these things. Let me bring it up here. Chapter 3, this is section 3.3. Somewhere down there. Yeah, we're close here. Where's it at? So right. Yeah, there it is. Down there. Ooh, be careful. Don't go too far. Don't go too far. Don't go too far. I went too far. There's my spring. Okay, I'm gonna bring this in. Send to a new page, sure. Whoa, that's big. So this is the 3 graphs: position, velocity, and acceleration. Let's analyze the behavior of this spring. Now think about it. If I've got the spring pulled 4 centimeters beyond its rest point, and as soon as I release it, now think about it. At time 0, is it moving yet? No. The velocity is at 0, right? As soon as I release that spring, it starts to move. How does it start to move? It starts to move back, right? The velocity is a negative velocity. It's moving in a negative direction. It's going up. It's going backward, right? So it's going back toward its original shape. And the acceleration is going down, right? Think about it. If I pull that spring as tight as I can, 4 centimeters past its rest point, there's a lot of acceleration acting on it, right? That spring wants to coil back. There's a lot of, what's that called? Potential energy, right? Not kinetic. Kinetic is. So a lot of potential energy there. So as soon as we release it, it starts to jump back up. And as soon as it jumps back up, the acceleration starts to dissipate, right? The acceleration starts to go away because it's coiling back up, right? So the acceleration starts to go back towards 0 right away. Right? Then the acceleration is going to continue because it's going to go back down to the ground, right? The acceleration due to gravity is going to work back toward it. And then it's going to go back and come back up again. So the acceleration is going to act back on it. So the velocity and the acceleration are, the velocity and acceleration are kind of like working backward on it, right? If I think about the velocity, I pull that spring, it's not moving, I let it go, it starts to move, and then at some point, once it reaches back coiled up, it stops moving again, right? There is an instance where it stops moving. What? I know, I changed that into my, it was bad when I took it. I had the same outfit on. Did anybody come and watch the dodgeball?
I saw. You guys did good.
We dominated.
Champion.
We dominated. It was not only good, we dominated.
Yeah, you're on the stage.
I want to see the live stream. I want to go back and watch.
Yeah, no, I'd like to watch film for next year. I think there's still ways to improve.
I would love to have a rematch over the Average Joe's team.
The first team took way too long to finish them off.
Exactly.
We need to.
Yeah. The German team, we finished them off quick.
German.
I know.
Good, dude. This is gonna be the best video ever.
We're talking about springs.
Spring.
Yeah. And we're talking about how if we take the derivative of the position function, we get the velocity.
Yes.
And if we take the double derivative of position, we get acceleration, right? So if I pull a spring,
Yeah.
and then I release it,
Yeah.
the acceleration starts to go away, but then the velocity starts to counteract on it.
Yeah, I got 'em right.
Yeah. Let's do one more problem, shall we?
One more what?
One more problem.
One more opportunity.
One more opportunity.
I'm so disappointed in you right now. You should have been all over that.
I'm sorry.
You got that right. On the 27th derivative. Oh, that's beautiful.
Find the 27th derivative of cosine. Now, because this is either a ridiculous question or there's got to be some pattern. You good there? Okay, just go ahead and turn them into the box and you guys can head out. Thanks. If I want the 27th derivative of cosine, there has to be some pattern, or I'm just asking you to, I'm just being mean to you, right? And you have to write it out 27 times. So long. See ya. Okay, so if I find the first derivative, let's call f of x cosine x, okay? If I wanted to find f prime of x, what is the derivative of cosine again? Negative sine, right? Okay, what's the second derivative? What's the derivative of sine? Cosine. Okay, what's f triple prime then? Right, so this is, what is the derivative of cosine? Right, so this is, the derivative of cosine is negative sine. So what's that reduced to? Positive sine. And what's the derivative of sine? Okay, we've gotten back to our original amount now, right? We've gotten back to our original value. What do I take? What happens if I take the derivative of cosine? Negative sine. What happens? So fifth derivative would go back here. Sixth derivative would be back here. Seventh derivative would be back here. Eighth derivative would be back here. This is, you know what this kind of works like? Powers of I. Like I to the first, I to the second, I to the third, I to the fourth, and so on. You good, Mr. Hudson?
No, I'm looking at the next screen.
Oh yeah. That's Monday's lesson.
Oh.
Yeah. So this is 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Do I need to keep doing this though? We could have found a pattern. 22, 23, 24, 25, 26, 27. So I ask you, what is the 27th derivative of cosine x? Sine x. Okay.
I saw it.
I saw the sign. I see what you did there. F27 of x would be, get us back to sine x. Yeah. Because it's cycles of 4. It'll go in cycles of 4. Right? It'll go in cycles of 4. So every time we find the derivative of sine, it gets us back to cosine in some way. And every time we find the derivative of cosine, it'll get us back to sine in some way, whether it's positive or negative. I think that's kind of cool. Again, it works a lot like powers of I. I squared is -1. What does it go? Positive 1, -1, positive I, negative I. It's like the cycles of I. Yeah. Okay. We've got 2 problems to do on Monday.
Cool.
That's it. 2 problems to do on Monday. The rest will be a work day. Code word for Max, like he's actually going to watch to the end of the video. Code word, Max. Max's code word is fluffy. If you walk in and say the word fluffy, we are going to look at you weird. And then we're going to remember that we said the code word. It's going to be fluffy. Okay. So long, Max.